Hello, my name is Joshua Weaver, and this is my coursework of a 3D model representing a scene of dinosaurs wreaking havoc in London for ECM3423 computer graphics. The scene is made up of different objects such as tanks, buildings, roads and dinosaurs, and is contained inside of a skybox. All four of the required concepts in the specification have been achieved. Lighting and illumination can be changed as seen here. There is also texture mapping on several objects such as the buildings and the Triceratops, as seen by its skin. Environment mapping has also been achieved, such as on this Velociraptor reflecting the skybox around it. And finally, I have an animated object which is on a loop and is able to rotate. Firstly, to enable the animated raptor, I use the lerp equation inside of my main file which runs the program, Jurassic.py. The linear interpolation equation can be expressed as a plus b minus a multiplied by t, where a and b are the initial and final values and t is the interpolation parameter ranging from 0 to 1. This formula calculates a smooth transition between the start and end values. I use some variables to store the information for the updating method for the raptor. As seen here, I've defined a start and target position for the raptor, as well as setting the current position to the starting position. I've also defined a lerp factor and a rotation to be applied. The raptor object is first loaded here through the load object file method, and afterwards drawn from its mesh seen here. In the update raptor position method, firstly, the lerp factor is incremented, and then if the lerp factor has achieved a rating of 1, then it's reset and both the starting and target positions are swapped, as well as applying a rotation to the raptor. Here the lerp equation is being applied, and finally the raptor's model matrix with translation and rotation is being applied to the raptor here. This is where the update raptor position method is being called from inside the draw method. For lighting and illumination, I'm first going to talk about the light source. Firstly, the light source class is imported to Jurassic.py. You can see here in line 9, it is imported from light source. It is initialized in the Jurassic.py constructor, shown here as self.light, and given a position in the scene through its parameters representing x, y, and z. Then a model is made from a mesh in the same location to represent the light source. This is self.showLight. The model of the light source is also drawn in the draw function of the Jurassic scene class. LightSource.py contains the class for handling the light source information. In the constructor, the ambient illumination, diffuse illumination, and specular illumination of the light source is defined. There is also a method to update the position of the light source if required. When we zoom out of the city, we're able to see the light source and the model that represents the light source. As we change the angle of viewing of the city, we can see the light reflections of this light source move around. Next, I'm going to talk about the shaders. GLSL is a specialized programming language used for writing shaders in OpenGL to define how light interacts with 3D objects and customize various aspects of the rendering pipeline, such as vertex and fragment shading. Vertex shading involves computing the attributes of vertices in a 3D model, such as their positions and colors, while fragment shading focuses on determining the final color and other properties of individual pixels. Shaders, the folder found here on the left, contains the GLSL code source for each shader program. You will see there are many folders here, including flat. This folder contains two files, vertexshader.glsl and fragment shader, that contain the programs for the vertex and fragment shaders respectively. Here they are. General workflow-wise, in the constructor for the Jurassic scene, we declare all of our models that are going to be loaded into the scene. At the end, we define a shader that we want to give to each of those models. These functions are imported from the shaders file here. In this file, the scripts load the GLSL code for vertex and fragment shaders from files or provides default code if the file paths are not provided, seen here. It compiles these shaders into a shader program. It manages uniforms, allowing for easy binding of different types of data. This is found in the uniform class here. There are special classes for specific shading models found at the bottom of this file also, such as Phong and flat shading. Here you can see the Phong class and the flat class, which both extend the capabilities of the base class for shading. The models file, shown here on the left, is used to hold both the object files and the MTL files for all the objects used inside the scene. The object file is a plain text file format that represents the 3D geometry, including the vertices, the faces, the normals, and the texture coordinates of the object. The associated MTL file contains the material definitions specifying properties such as color, reflectivity, and most importantly, the texture maps for the surfaces of the 3D model described in the corresponding object file. For example here, with the 3roads.mtl, we are mapping a texture called r1.bmp onto the object. Found here, r1.bmp shows the road. This is how texture mapping is done. Out of all the objects rendered into the scene, we saw that one of the raptors used environment mapping instead of Phong shading as the rest. We see this declared here as the shader as environment shader, map equals self.environment, instead of shader equals Phong shader as the rest. This is imported here through environment mapping file on line 23. Inside the environment mapping file, we see the environment shader class. This inherits from base shader program and represents a shader program used to render an environment map. The constructor initializes the shader with a name and an optional environment map. It binds the shader to a model and sets various uniforms such as the cube map sampler, view matrix VM, inverse transpose view matrix view MIT, and the transpose view matrix VT. The bind method takes a model and its model matrix as the parameters. The environment mapping texture class shown here inherits from cube map and represents a cube map for environment mapping. The constructor initializes the cube map with a specified width and height, shown here as 200 and 200. It contains frame buffers, FBOs, for each face of the cube map, shown here, and defines transformation matrices for each face, views, here. The update method is used to update the cube map. It renders the scene from each face's perspective to generate the environment map. It modifies the protection matrix P, here, and a viewport to render the scene from different perspectives. The cube map is rendered face by face using frame buffers, and the scene's camera is updated accordingly. All objects inside the scene inherit from the base model class found inside the basemodel.py file. The constructor initializes the model with specific parameters, including the scene, the model matrix, the mesh, color, and visibility. The initialize VBO function initializes the vertex buffer object for a given attribute's name and data. The bind shader function binds a shader program to the model, handling shader compilation and attribute binding. When the bind function here prepares and stores vertex data in VBOs for GPU rendering. The draw function renders the model using OpenGL functions, considering visibility, shaders, and mesh data. And finally, the VBO.del function releases VBO objects when finished. The draw model from mesh inherits from the base model class, inheriting both its attributes and methods. The constructor extends the base model constructor, initializing the model with additional parameters specific to drawing models from a mesh. The overall purpose of this class provides a specialized version of a 3D model that is particularly tailored for rendering meshes. This Blender file contains functions for loading the Blender 3D object files found inside the Models folder. Process line function processes a single line from the Blender file. It identifies different types of lines such as comments, vertices, vertex textures, normals, material libraries, materials, and faces. It returns a tuple containing a label and the corresponding data, shown here. The load material library reads a Blender material library file and creates a material library object. It passes the material definitions, including ambient diffuse, specular relativity, illumination, and texture information. And here. The load object file function reads a Blender object file passing the vertices, faces, materials, and texture information. It uses the process line function to handle different types of lines in the file and creates a list of mesh objects using the extracted data. Done down here. The create meshes from Blender function takes a list of vertices, faces, materials, texture vectors, material library, mesh list, and line numbers to create a list of mesh objects. It uses the information to organize the data into individual meshes based off the material. The create mesh function uses a single mesh object from a subset of vertices, texture, vectors, faces, material library, and material information. And finally, the fix blender method corrects the indexing of textures in Blender files for OpenGL compatibility. Inside scene.py, we see that a camera gets initialized on line 77. This comes from the camera.py file, which imports the camera class. This is a simple class which is used to represent a camera, with the constructor, where the distance of the camera to the center point, as well as other variables, is being defined. There is also an update function which applies matrices to the camera in order to position it correctly. Inside the camera file, you see that we import a bunch of functions from a file called mat-utos. Inside this file is a collection of useful matrix utilities for 3D graphics. Firstly, we import numpy as MP to use inside of these functions. We have a scale matrix, a translation matrix, and a rotation matrix for different axes such as Z, X, and Y. We also have a pose matrix, an ortho matrix, and a frustum matrix. Finally, we have some homogeneous coordinate helpers. CubeMap.py is a file that contains the classes for handling cube maps and rendering the flattened cube map onto the screen. The class flattened cube shader is a shader program for drawing a flattened cube map onto the screen. This inherits from base shader program. The sampler cube is a uniform variable representing the cube map, as shown in this final line, self.addUniform sampler cube. Flattened cube map's purpose is for drawing flattened cubes on faces onto the screen, mainly used for debugging purposes. This inherits from the draw model from mesh. Attributes: the scene object is scene, cube is an optional parameter for the cube map texture for draw, and vertices and faces are arrays representing the flattened cube. The cube map class is defined for handling cube maps. This inherits from texture. The name is the name of the cube map, and the files are a dictionary containing file names for each face of the cube map. Here in self.files, we have defined the names of the BMPs which are going to be used for the cube map. These files can be found in Textures, Skybox, London. These are used for the Skybox. As we are discussing the Skybox, I'm going to quickly discuss the Skybox.py file. Inside this file we have two classes, a Skybox shader which is responsible for the shading of the Skybox, and the Skybox class itself which inherits from the draw model from mesh. Inside you can see that we define where we would like to find the textures for the Skybox, Skybox London, inside texture. You can see that this uses the cube map class. The mesh.py file imports both a texture class and a material class. The mesh class is used to represent a mesh that happens in the scene. It has a function calculate normals, which calculates the normals for the mesh if the normals are not provided. It also has a class of cube mesh to represent a cube mesh. Inside scene.py we have the scene class. This is what Jurassic.py inherits from. In the constructor, we define several variables which are relevant to the scene, such as width and height, and initialize Pygame as OpenGL was unable to draw to the screen itself. We have several GL functions which change the attributes relevant to the screen, such as size and color of the background. We also have several functions such as add model and add models lists, which adds model to the list in the scene, and we also have a draw function. This draws to the scene, but uses a frame buffer to flip so we don't see the drawing itself happening. We also have Pygame events. These respond to events that happen on the screen, such as pressing Q to quit and a mouse down button to move around the camera. Finally, we have a run function. This is a function that continuously loops over and over while the scene is running. We also have a frame buffer class which is kept inside framebuffer.py. This is a basic class used to handle rendering to texture using a frame buffer object. It has several methods such as bind, unbind, and prepare. Jurassic.py is the main file of the program. It contains the Jurassic scene, which is inherited from the scene class. We've already gone through much of the functionality in which we create these objects from loading the object files from the models folder. Here we have a draw function which draws the objects to the frame buffer and then once drawn flips the frame buffer so we are able to see the models. We have additional keyboard functionalities to press on screen which perform showing textures and showing the flattened cube map. Finally, we have the main function which loads the Jurassic scene and then runs it.